Good morning, colleagues. Given the international drive to use reforestation as a restoration tool, I'm going to be reflecting on the long, rich history of research in South Africa on the impacts of trees on hydrology and the lessons that can be taken from that research. To start, some context. Water is considered one of South Africa's key limiting factors for economic development. Our rainfall is lower than the global mean and highly variable both spatially and temporally. On average, less than 9% of our rainfall is converted to streamflow, as a large portion of rainfall is partitioned to evapotranspiration. Thus, any change in land use or land cover that alters the transpiration component alters the water balance of a catchment, meaning any land management decision is a water resources management decision. Different land uses have varying impact on the hydrological cycle, with some having a far greater impact than others. A key land use in the South African case is forestry. Looking to the history of forestry in South Africa, in 1850 the idea that planting trees would increase rain in dry areas was first promoted, although questions soon began to be raised about the legitimacy of this. Promotion of this idea continued until 1935 when the British Empire Forestry Conference was held. At this conference there was significant public and scientific criticism of forestry, which led to support of the establishment of a research program to investigate the impacts of trees on water. The first forestry research catchment was established in Jonkershoek in 1935, outside of Stellenbosch in a winter rainfall area. Later, in 1945, the Cathedral Peak Research Catchment was established in the summer rainfall area in the Drakensberg. Further research catchments followed. The research catchments were designed as pair catchment experiments, where catchments with similar climate, soils, and other characteristics were delineated. Monitoring was initiated in the catchments, and following a short period, the land cover of one of the catchments was changed while the land cover of a benchmark catchment was held constant to allow for comparison. For example, in the Cathedral Peak area, catchment 2 and 3 were planted to pines, while catchments 6, 5, and 4 were held as grassland catchments to allow for comparison. Significant thought was put into the rainfall and streamflow monitoring, both into the design of the equipment that was used for the monitoring and into ensuring that the quality of the data from the experiments was good. This led to a high level of confidence in the data and the results from the experiments. The influence of trees on streamflow was evident quite quickly. Shown here is a graph produced by Nanny in 1970 for the Cathedral Peak catchment. The top set of lines are the rainfall recorded, and the bottom set are the runoff. The solid line is catchment 2, the long dashed line is catchment 3, and the short dashed line is catchment 4. Over time, the pattern in the rainfall recorded in the three catchments remains constant, with catchment 2 recording the most rainfall and catchment 4 the least. The pattern in runoff, however, does not remain constant. In 1950, catchment 2 was planted to pine. With the establishment of the pines, the decline in runoff over time can be seen to the point that the runoff of catchment 2 is below that of catchment 4, which receives less rainfall than catchment 2. Catchment 3 was planted in 1958, and by the end of the record shown here, it can also be noted that the runoff from catchment 3 was below that of catchment 4. What causes this significant influence of forestry on streamflows? There are three key points in the hydrological cycle where the influence of trees is great. At the canopy, where the trees intercept more rainfall than the vegetation they replace. At the soil surface, where the litter layer under the trees alters the infiltration runoff partitioning. Under the trees, the infiltration rate may be higher, but there is far less water available to infiltrate. And then at the root zone, the trees are far deeper rooted than the vegetation they replace, allowing them to access deeper soil water reserves and in some cases groundwater. Added to this, the higher aerodynamic roughness of the forest canopy enhances the evaporation process. The commercial trees are fast-growing, evergreen exotics. They typically replace shorter indigenous vegetation that senesces during the dry season, which means the impacts of the trees are particularly great during the dry season, when the trees continue to transpire and the indigenous vegetation has senesced. The results from the research catchment studies had clear lessons for policy. Limitations were placed on where forestry could be grown, and longer rotation lengths were preferred over shorter rotations. Policy uptake followed, with the afforestation permit system being implemented in 1968. This permit system made use of the nanny curves to estimate the reduction in runoff due to afforestation. Research continued alongside the implementation of this permit system, and in 1972 a further policy which restricted forestry in riparian areas was put into place. Today, under the National Water Act of 1998, commercial forestry has been declared a streamflow reduction activity, which means a water use license is required for commercial forestry growth. Currently, it is the only streamflow reduction activity that has been declared under the National Water Act. Although field-based catchment research has ceased over time, the declaration was premised on good field-based observations, and the data from the research catchments continues to be used through modeling-based studies to develop tools to support the implementation of the National Water Act. The results and data from the forestry catchments experiments have also been used in other areas, such as by Lemaitre in estimating the reduction in runoff due to alien invasives. However, where we stand now, the questions around forestry impacts and other land use impacts on water have become more nuanced, with global change, both climate and land cover, leading to increased pressures on ecosystem services, combined with the complex socio-ecological challenges we face in the South African context. There's a clear need for mitigation and adaptation and for restoration. Reforestation is being pushed internationally as a means for carbon sequestration and restoration. However, the South African research is clear. Trees have a significant negative impact on South Africa's water resources, and the myth that they create rain has been dispelled. But this historical research is not sufficient to answer the more nuanced questions that are arising today. Therefore, there is a need for more research. We have a limited understanding of indigenous tree water use. Recent studies show that indigenous tree water use is lower, but this is based on very limited data of less than 1 year. Initial results on woody encroachment water use in the Drakensberg are showing a higher total evaporation from the woody vegetation in comparison to the grasslands, and a reduction in streamflow over time. But again, this is one site and a limited period of time. What is known is that 60% of the national carbon stock is found in grasslands, with 89% of the carbon stock in the soil. Unlike trees, 2/3 of grassland productivity is underground, with an extensive amount of carbon stored underground as opposed to above ground. What we also know is that greater species diversity leads to a greater soil carbon storage, and a greater soil carbon storage leads to a greater soil water retention. What is also known is the water-stressed nature of South Africa. Approximately 50% of South Africa's water is produced from 9.8% of the land area. Areas identified as strategic water source areas. Further to this, 98% of South Africa's readily available surface water is already used. To be able to maintain the water produced from these strategic water source areas, healthy, biodiverse ecosystems are required. However, according to Lemaitre, only 10% of the strategic water source areas fall within protected areas. The land cover in large parts of many strategic water source areas has been significantly altered by anthropogenic activities, with extensive areas in some strategic water source areas becoming severely degraded. Further to this, a number of the strategic water source areas fall within the grassland biome, where internationally it has been suggested that reforestation occurs. Internationally, restoration is often synonymous with reforestation. In our context, this cannot be the case. The myths that afforestation are good for water have been debunked in the South African setting. The implications for water need to be considered in restoration activities in South Africa. In our context, restoration for ecosystem resilience is required. In order to protect ecological integrity, there needs to be a nexus approach taken where biodiversity, carbon, and water, in the light of socio-ecological challenges, are considered. And there needs to be an understanding of the interactions and feedbacks in an integrated manner. To be able to undertake a nexus approach to restoration which promotes resilience for the most vulnerable in society, we need collaborative, long-term observation science under changing conditions to provide South African context-relevant information to inform our restoration decisions. And in this light is not only the results from the historic forestry research catchments where lessons can be learned, but also how the trust in the forestry impacts research was established. Through the thoroughness of the research and the patience that was shown, these experiments were not short-term, they were long-term experiments, and the relationships between the stakeholders at all levels that were established during the research. And often those relationships had better results than any policy briefs that resulted from the research. Thank you for your time.